Okay guys, we're going to speed through the first part of this chapter 20 notes. Pause if you need to catch up. Got to try to fit it in 15 minutes or less. So chapter 20, we just kind of reinforce some ideas that we learned in chapter 19 and then add a couple more key terminologies and concepts. First of which is a p-value, which we met in chapter 19 but we're still having some trouble with. First of all, you need to understand that you only get a p-value when you run a hypothesis test. So it doesn't happen in a confidence interval, not a worry there. Because a p-value is associated with the probability of getting a certain kind of sample. So you run into this when you do the mechanics of a hypothesis test. So in general, let's just rehash it. In general, if the null hypothesis is true, so which is what we always start off assuming, then it's the probability of observing a sample at least as different from the hypothesized value. Hypothesized value of P. So little p, the percentage of people who do something, the percentage of things that haven't changed, from the hypothesized value of P as what we got in our one sample. This is not in context, so we would have to do this in context of a real world problem. I always start with a conditional, that way I don't forget that it is a conditional probability, and everything hinges on that assumption that the null hypothesis is true and our goal to find evidence that it's not. In context, we could see something like this problem. Have harsher penalties and ad campaigns increased seatbelt use among drivers and passengers? Observers of commuter traffic failed to find evidence. Failed to find evidence means we did not have enough evidence to reject the null of a significant change compared with 3 years ago. Explain what the study's p-value of 0.17 means in this context. Okay, so the big idea is we have some population percentage p, and then we took a sample, and that sample is looking for evidence of a change, either an increase or a decrease. So somewhere we picked up a sample that was either up here, higher than the true p, or down here, lower than the true p, because we're looking for a change, which means we could go either direction. So if we total up those two areas, we would get an area of 17%. That's what that p-value 0.17 means. So if, in fact, the rate of seatbelt use has not changed, that's our conditional. So this is our in context null is true. The rate has not changed. The probability of observing a sample, I wish we had our sample p hat. We don't know that number, but whatever p hat was that landed here or here somewhere, the probability of observing a sample p hat at least as far from the p, and normally I would know that number, so I'd put that number in, at least as far from p as our sample is 17%. It's easier to write this if we have a stronger context. If we know what p hat is and we know what p is, we know the true proportion, we know exactly where our sample landed, we can substitute those numbers in and it makes our context clearer than it is here. The catch is, in a multiple choice question on the AP exam, you have to pick the one that's a conditional probability and it's about how different the sample is from the proposed parameter P. Okay, now for some new things. An alpha level of the test. So this is a new term. Alpha is a Greek letter. The lowercase alpha looks like a side, well, if you think about our lowercase a, this is the Roman lowercase a, this is the Greek lowercase a, they're quite similar. So alpha is the name given to the threshold value beyond which we would reject a null hypothesis. What does that mean? Okay, so let's say we have some proposed P in our null hypothesis claim, and we decide that past a certain point, if P hat lands at that point or beyond, we're going to reject the null hypothesis. That cutoff is called an alpha level. So if there's, say, 5% of area here, we would say that our alpha level is 5%. So it's whatever cutoff we define for how we're going to reject that null hypothesis. We've been using 5%, but this is really flexible. We could use 5%, we could use 10%, we could use 2%, we could use 1%. So it's a choice unless we're told otherwise. So we'll define this as the threshold p-value below which we would reject the null hypothesis H naught. So if our p-value is below 5%, so it's 4%, 3%, 2%, 0.0003, if it's lower than 0.05, we would reject the null. If it's higher than the alpha value, we would fail to reject the null. So it's that cutoff point that we define before we make a decision. If we aren't given a specific alpha level on the AP exam to use, we pick our own. 5% is the most typical value. Another name for the alpha level, you'll see this occasionally, just a terminology. It's also called the significance level, because beyond that level, beyond that 5% marker, is where things get statistically significant, where things get interesting enough, unusual enough for me to begin to doubt that null hypothesis. Which brings us to the next term. Well, that's actually a couple slides from now, so we'll get to it. Okay. So a question about that alpha level, you'll see something like this perhaps on the AP exam, and I think a picture is probably the best way to deal with it. Environmentalists concerned with the impact of high-frequency radio transmissions on birds found that there was no evidence of a higher mortality rate among hatchlings in nests near cell towers. So we were looking for evidence of a higher mortality rate, but we didn't find it, which means we failed to reject. So no evidence means we did not reject the H naught. They based this conclusion on a test using an alpha level of 5%. Okay, what does that mean? Let's look at a picture. Picture's probably the best tool that you have. All right, so there was some proportion of hatchlings that die in the general population of birds. And then there was some sample of birds that was taken, and the decision was made before the sample was taken that at an alpha level of 5%, if we had a sample that landed higher than that threshold, in other words, if our probability was less than 5%, we were going to reject. So this is reject zone over here in the tail, and any sample that lands over in here would be in the fail to reject zone because it's not high enough to argue that there's a higher mortality rate for those birds. So what we know is that here is not where the sample is. So the sample is not here. I don't know exactly what my sample was, but I do know if there was no evidence and I didn't reject, my sample didn't land in the tail. My sample landed over here somewhere. So the sample is in here. I don't know where. The sample could land here, 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 here. Anywhere in that region is where the sample could have been. It could have been below the P, above the P. It could be really, really close to this alpha level cutoff. I just don't know for sure. Okay, They based the conclusion of the test on the alpha level of 5%. We want to know if they would have made the same decision at 10% or at 1%. So let's take a look at those. At 10%, well, alpha equals 10%, it means we would reject if our probability was larger. We would reject if the alpha level was smaller than 10%. Well, if 5% of the area lies in this tail, if we go just a little to the left of that, then 10% of the area can lie in here. It may not be drawn to scale, so it just isn't. Alpha is 10% there. So now we have a larger reject region. We have more place where we could reject the null. Now the sample, I know, is somewhere in here. Somewhere in this region is where my sample fell. That sample could have been in this big part, or it could be in that little sliver right there. If the sample landed over here, we would have kept the same decision, not reject. If the sample landed here, we would have changed our decision and rejected the null. So at alpha equals 10%, the decision may have been the same. But we don't know for sure, and we'll never know, because we're not sure where the sample is, if it's here or here. They didn't give us that information. On the other hand, at 1%, if we go to where 1% of the area is, do this in a different color, do some pencil. Let's say that alpha is 1% there. Okay, now reject zone is out here in this little tail. And I know for sure that my sample was in this shaded region over here, which means my sample was closer to P than that cutoff. So my p-value, being bigger than 5%, certainly can't be out here in this outer 1%. So because the p-value is to the left of that alpha level, then I would still not have rejected at alpha equals 0.01. So at alpha equals 1%, the decision would be the same. I would still be in the not reject region with my sample, because I know my sample's not over in here. Which brings us to the idea of statistically significant. A statistically significant result in hypothesis test means that we have a sample that lands far enough out in the tail to reject the null. So to be statistically significant means that we got a p-value smaller than the alpha level. So we rejected the null hypothesis. So to be significant means that we found enough evidence of a change to be able to say there's something going on. All right, critical value. Let's stop, since I'm close to 15-minute mark. I'm going to stop the video and we'll pick up with critical value on the next segment.